Hello and welcome to this presentation at the Electronics Asia 2023 online conference. My name is Allan Fredriksson. I'm working at Cambridge GaN Devices in the role as Vice President of Research and Development. In this presentation, we'll introduce you to how GaN can fulfill the data center demands for efficiency and power density. If we take a look at some of the mega trends in society that is affecting semiconductors, we can see four megatrends that has a significant impact. Of course, on semiconductors, as well as many other aspects of society and our lives. From increased focus on climate change, driving focus on energy efficiency, to urbanization, driving, for instance, Internet of Things for smart cities, to increasing population that increases the general demand for devices, services, and energy. And not to forget, digital transformation, the digitalization and trends for big data, machine learning, and artificial intelligence that is driving computation needs higher and higher. And this is the topic we want to look a bit further into in this presentation, where the focus is on data centers that enables the digital transformation. If we look at what's powering the digital age, we see that this megatrend on digitalization is predicted to lead to a massive increase in electricity consumption in the data centers. A lot of the digitalization will have devices, there will be Internet of Things, but it will also run in the cloud and run in data centers. So more than a factor of 6 is anticipated in electricity consumption from 2018 to 2030. And also even proportionally, this is becoming a major factor of global electricity consumption, as the data center increases its share of total electricity consumption from around 1.7% in 2018 to a massive 8% in 2030. This is massive, and we think this requires action. Before we talk a bit about the action, I want to talk a bit about trends in data centers. So if we take a look at what is happening in data centers these days, we can formulate the following trends. There's the agile, scalable infrastructure for easy management, expansion, and integration of equipment into data centers. This has been ongoing for a while. There's the open compute framework, there's a common redundant power supply framework, there's several initiatives industry-wide to make sure that there's an agile and scalable infrastructure to meet the increased demand and for computing in data centers. And soon we will take a look on the next slide at the typical electrical distribution architecture for data centers. But before we do that, there's also the topic of high density computing. It's of high focus because in order to put more and more computing power in the same space and not build new buildings for new data centers continuously, as the demand for computing power increases dramatically with the AI trends in many industries and applications. And that's one of the key trends as well, which is also driving power density as a key element in the power supply. Also, advanced cooling techniques starts to be taken into use to keep equipment more cool so that it is effectively cooled while it's packed more densely. And then, of course, there's the overarching theme of sustainability with an increased focus in society, also from corporations, on net zero goals and achieving those. And that's moving in various industries at the moment. Okay, but now let's take a bit more practical look. What does this mean? So if we take a look at data center power supply architecture, you will see a typical power supply architecture here. For scalable and agile infrastructure, there's this power distribution architecture in a server rack from the AC supply point going in to the point of load where the action happens, where the computing happens, where the value is generated of the data center. It has multiple conversion stages. You see it first converging from from AC to DC in a power factor correction stage, and then it gradually brings the voltage down first to soft 48 volts, down to which then distributes within the rack, and then further down to 12 volt on this individual server unit, and then as close as possible to the point of load, bringing the voltage further down to the required voltage for the CPU, the GPU, the NPUs. And this is then where the processing happens and the function of the data center is fulfilled. There's of course different trade-offs involved in how many stages and how efficient each state then correspondingly can be. So there's always a trade-off. And there's, for instance, explorations in the next mainstream architecture for data centers, possibly to remove the IPC stage. Overall, the key technical requirements beyond scalability is efficiency, power density, but also robustness and reliability. And this is where GaN comes into the picture. It holds the key to make step function improvements in data centers on these technical requirements. It will allow a new level of power density and efficiency in each of the stages you see on this slide. And while there has been robustness and reliability concerns related to GaNs, E-mode GaNs, the power switch itself, CGD has introduced iSCAN, which combines the power density and efficiency benefits of GaN switches, and at the same time, maintaining or even exceeding the robustness better than silicon solutions. How does it do that? Well, let's first take a look at what it means in terms of the data center, and also how it then achieves this. You see some of the key points here. Traditional silicon devices are limited in switching speeds, and which leads to higher energy losses, as well as bulky passives for the required power. With GaN, one of the benefits is that it can maintain or sustain much higher switching speeds of the power supply, and this leads to smaller passives and smaller heat sinks, also due to the benefits of GaN itself, the higher figure of merits and serial reverse recovery is a couple of examples when comparing against silicon. So with the properties of GaN switches, in addition to what it was mentioned already, you see the max benefit coming into use on the right side, when it enables also new and more efficient topologies, like for instance in the PFC stage, the use of totem pole PFCs. So this leads to all these elements to something like a factor of 3 possible in power density and a 40% reduction of losses in the power conversion stages. So this is massive. Let's take a look at what iSCAN is. As mentioned earlier, GaN has clear advantages for power density and efficiency, but in terms of robustness, special care must be taken. That's why Cambridge GaN Devices developed the iSCAN concept that monolithically on the same die as the GaN power switch introduces several things. First of all, it enables ease of use, or as we like to say it, drive it like a MOSFET. So it should be very familiar for power supply designers that can easily start adopting GaN and using GaN instead of silicon. And at the same time, this circuit has all the required protections of the power hemmed gate monolithically integrated, which leads to best-in-class robustness, which removes a major headache for power supply designers adopting GaN in their designs. And we'll now take a look at a couple of examples of both these elements. So if we take a look at the robustness, you can see an evaluation done here by a well-known research institute in power electronics, Virginia Tech. You see that iSCAN gives extreme robustness against dynamic voltage overshoots on the gate terminal, and compared to a state-of-the-art E-mode GaN, it's a factor of 3 higher. This is massive, and this brings iSCAN and GaN with iSCAN on par or better than state-of-the-art silicon devices in terms of robustness against dynamic overvoltage on the gate. And this kind of robustness is of course important in all applications of GaN in power supplies or power supplies in general, but it's of particular value in high power applications. The currents are much higher, there's a much higher incidence rate where you will see these kind of things happen, like in a data center power supply, which is why it's a crucial point for enabling GaN easier of use into the data centers. If we look at the core benefit of GaN and iSCAN, we here have a benchmark where we took one of the power stages, the PFC stage, in a data center electricity distribution system. And you can here see the full benefit of GaN, both taking advantage of advanced topologies and of course higher switching frequencies and the higher figure of merits and other things that the GaN switch itself provides. And this results in a 40% reduction of the loss in the high power stage. This is massive, and this by itself shows why we now see GaN moving into the data center power supplies. And with the concerns on reliability and robustness addressed with iSCAN, there should be no reason not to move this direction. So overall, to wrap up, GaN is leading to increased power density and energy efficiency, enabling more compute power and memory per server to fuel the AI revolution, the data center evolution, and the massive growth in data centers that we expect over the next decade. It enables data center operations to meet constantly tightening regulatory requirements, as well as an increasing push from various industries, companies to work towards net zero goals. And this also helps keep the data centers cooler. And with the iSCAN robustness is integrated on the die itself to make sure you don't need to worry about meeting uptime requirements. So overall, GaN enables sustainable data center operations, which is becoming increasingly important for overall worldwide sustainability. And what if all data centers were to adopt GaN? We did a calculation based on various sources, based on our assessment and looking at what is published out there on what can be achieved. You see the results here. GaN in data centers, if it's adopted fully, will lead to a massive saving on electricity and also a massive reduction in the associated metric tons of carbon dioxide emissions. And with this final statement, I would like to thank you for your time. Should you have any questions, do not hesitate to reach out either directly to me or use contacts you can find via our website. Thank you very much.